Alright, so in this video, we're going to start with the idea of thermochemistry, which looks at changes in energy that accompany chemical reactions. And specifically, we're going to look at a couple of types of energy. We're going to look at heat, and we're going to look at the idea of work. So if you remember from thermodynamics, you've probably seen before, there are three main laws of thermodynamics. The first one being the law of conservation of energy, or conservation of energy and mass. So this says that the universe has a constant amount of energy that we can convert between one energy type or another, but we can't create energy out of nowhere, and it can't disappear into nowhere. So some common ideas that we have about converting energy, of course, in our bodies, converting food into energy of motion. So putting gasoline in our cars to combust in order to get motion from our car. Solar power, solar energy being used by plants to create chemical energy. And there are several other examples. So we're going to look at how we can see this transference of energy. When we calculate the total energy for a system or a process, it's called the internal energy, or capital E. And this is really all of the energies combined. So frequently there's more than one energy involved in a system. For example, heat and work that we're going to look at. But mostly people define energy based on kinetic energy and potential energy. Kinetic energy is the energy of motion. It's the energy we have because we are in motion. Potential energy is the energy that exists because of position or composition. So if we pull the string back on a bow, even if we're not moving and holding it very still, there's a lot of potential energy because of the positioning and the tension in the strings. Pulling back a wrecking ball, it's the same idea. There's a lot of potential energy even if we're holding it still, because as soon as we let go, that potential energy gets converted to kinetic energy. So we're going to look at thermodynamics for a chemical reaction. And thermodynamics means the transfer of heat. Okay, so that's our translation of our word. So if we look at this transfer of heat, we need to define a few things. The first is, what are we transferring to or from? So we define these as the system. Our system is going to be what we're using as our desired reaction, or a balloon, or a piston. So whatever we're interested in is considered our system. The surroundings is then going to be everything around our system. That can be the air, that can be the tabletop, that can be the beaker the reaction is in. All right, so that is defined as the surroundings. For most processes, we have to take into account the system and the surroundings to define our universe. So the universe is our system plus our surroundings. So when we talk about heat transfer, we're talking about transferring heat from a system to the surroundings, or from the surroundings to the system. So the total heat in the universe remains the same, but we can see the transference. All right, another way to think about this has to do with looking at the total energy of initial state or initial conditions versus final state or final conditions. So in this visual, it's set up as a graph where we have internal energy along the y-axis, and then we might have progression of our reaction along the x-axis. So if we look at progression of a reaction, a chemical reaction, turning our reactants into products, we can consider our initial state to be the reactants, and then our final state could be the products, and we can see the amount of energy changing as our energy is transferred. So in this graph on the left, if our initial state or our reactants have more energy than our final state, then we have lost energy from the reactants going toward the products. So we say that energy is lost to the surroundings. So our system lost energy. That energy is transferred to the surroundings. The graph on the right shows the opposite idea, where our products or our final state have higher energy than our reactants or initial state. So in this case, energy had to be gained from the surroundings into the system. All right, so we would say that we have an influx of energy into the system that came from the surroundings. In either case, we can define the change, delta E, the change in energy for the system, by defining the energy in the final minus the energy in the initial. Alright, so there's a few different types of systems that we want to look at then. The first is a completely open system. If I have an open system, we can imagine a beaker with a chemical reaction in it, and there's no lid on the beaker. So it's completely open between the system and the surroundings. Therefore, I can transfer matter. For example, I can create a gas in my chemical reaction, and the gas transfers into the surroundings. So that would be a transference of matter. And I can also transfer energy. So heat can be lost from the system, lost from the reaction, going toward the surroundings. A closed system only allows for the transfer of energy. So imagine that same beaker with a chemical reaction, but now there's a stopper or a lid on it to prevent the transfer of matter. So it would prevent my gas from coming out of the beaker. So we can still transfer energy. Heat can still be lost from the system or gained by the system. In the third type, we have an isolated system. Isolated systems do not allow the transfer of matter or energy. All right, so in this case, the total energy of the system remains constant. We can calculate this change in energy by looking at heat and work. Heat and work are the ways that energy is transferred between the system and the surrounding. So here's our equation that we're going to be looking at. Energy is equal to Q, which is our heat, plus W, which is our work. So when we look at the changes in the amount of heat in the system and the amount of work done by the system or to the system, we can see the overall change in energy. Alright, so heat, or our Q, causes a change in the temperature when we have heat lost from the system or heat gained by the system. We're going to see that in terms of a temperature change. And typically we use energy units to define this. So energy units being our joules or kilojoules. All right, so you'll see this written as joules or kilojoules for our units. Our W is work, and work we're going to look at in terms of pressure volume changes. So we'll get to that. But work is also defined in energy units. So we're going to see work also defined in terms of joules or kilojoules. For pressure volume changes, we're also going to see it in liter atmospheres. Work is the energy transferred when an object is moved by force. With our PV work, or pressure volume work, we're going to see that force applied based on expansion or compression of a gas. Alright, so let's look at heat first. We know that heat transfers from a warmer object to a cooler object. Alright, so when we look at how heat is played out in energy transference for our chemical reaction, we have an idea of which direction that's going to go. And we're going to talk more about that reaction direction later. Work can be defined based on force times a distance. So if we're looking at how much work is needed to be done, we have to look at how much force we have to put in to do it. This can imply how heavy an object is to move. And we have to multiply that by the distance we have to apply that force. How far do we have to move that box? So this would give us work defined in joules, or energy requirements. We're going to look at it in terms of a gas doing the work, either expansion or compression. Alright, so for our delta E equation then, we have heat and work, so our Q and W. So we have to look at these independently. Heat can come into the system, or heat can leave the system. Work can be done on the system, or work can be done by the system. And whether we have heat going in or out, or whether we have work being done to or on, defines the sign of the Q and the W. Alright, so if I have a positive Q value, that means heat is absorbed. So I had to put heat into my system, therefore I'm adding the heat, so that's a plus, positive Q. Negative Q means that heat was lost, so heat would be transferring away from the system into the surroundings. Since heat is lost, subtracting heat, that's the negative. Alright, so positive Q means heat is absorbed, negative Q means that heat is lost. For W, our work, we also have positive and negative. Positive W means work is done on the system. Alright, so that means work is being done by the surroundings on the system. Negative W means that work is being done by the system. So the system is doing the work to the surroundings. Alright, so positive W means the surroundings are doing the work on the system. Negative W means the system is doing the work on the surroundings. Alright, so when we look at how heat and work changes will affect the total energy of the system, we also need to think back to our idea that changing energy was really just the final state minus the initial state. Okay, if we look at this equation, that implies that all I need to know is how much energy I had at the beginning and how much energy I had at the end, and subtraction will get me the change. So it means that it doesn't matter how I got to the products or how I got to that final state. It doesn't matter what method I used, what reactions I used. Alright, all it matters is how much energy I had at the beginning and how much I had at the end. This idea is called a state function. State functions are functions that only rely on the initial and final state and do not depend on the pathway or the route that was taken to get there. The other option is the path function. In the path function, it matters how you get from the initial to the final positions. Okay, the path matters, the route matters, the steps you take matter. So we have state functions versus path functions. So let me give you an example of the difference here. Let's say I have gasoline. So this is really octane, but we're going to say that's gas I can put into my car. My car can then combust the gas and convert a lot of that into heat and energy, all right, to allow my car to run. So if I do that option, I put the octane into my car, combust the octane, creates a great amount of heat, and also creates a great amount of energy that can be used to propel my car. So over here, I'm losing some of that as heat, but I'm also allowing the system to do the work. All right, so we see changes in heat, we see changes in work. Now if I follow the other path on the left here, and I take all that octane and I put it in a giant barrel and I set it on fire. All right, still combusting it, but now all I'm doing is creating a large barrel fire. This does not allow me to do any work with the octane, and instead I just create a lot of heat. So all of my energy is transferred as heat. All right, so depending on which path I take, whether I put it into my car or decide to put it in a barrel and set it on fire, definitely affects how much heat I'm creating and how much work I'm doing. All right, so putting it in my car, I see a change in the work and a change in the heat. Putting it in the giant barrel, all I have is a change in heat and there's no change in the work. All right. But also notice that I started in the same position, same amount of octane for either choice, and I finished in the same position. The octane ended up being combusted, so the overall change in the energy was exactly the same. So energy is a state function. It didn't matter which path I chose, putting it into my car or setting it on fire. The change in energy is exactly the same. But the path function we see for the heat was very different depending on which thing I decided to do. I produced more heat by burning it in a barrel compared to the heat that I produced by combusting it in the car. So my Q values would be very different. My W values would also be very different. Putting it into the barrel and setting it on fire does not give me any work. Putting it into the car, I'm able to get some work out of it. So our Q and our W are path functions. Our energy is going to be a state function. All right, here's another example by looking at water. So in the middle here, I have water at 25 degrees Celsius, which is room temperature, 50 grams of the water. Now, how did I get that water? I can start with 50 grams of ice at 0 degrees Celsius and then let it melt. All right, so melting the ice into liquid until it's all completely melted. That would give me this picture in the middle. Or I could have started out with water that was about boiling and allow it to cool down to room temperature. All right, it doesn't matter which one I chose to do, starting with ice or starting with the boiling water. Over time, I end up with the same 50 grams of water at 25 degrees Celsius. And once I have that water at 25 degrees Celsius, it is not possible to figure out whether I started with ice or I started with boiling water. All right, so the internal energy of the system doesn't matter the path I chose. It only matters where I start and where I end. The energy difference is going to be the same. But heat and work are path functions. So heat and work are not the same and will change based on the path you use or the steps required to get from your initial state to your final state. This shows an example with batteries. If I put the battery into a drawer and forget about it, it will eventually discharge over time, and I will have gotten nothing but an overheated battery, possibly some damage to my drawer, but no work done from the battery. If, however, I put the battery into an electronic device like a fan, I can get work from the battery. Either way, I'm going to lose the energy in the battery. Am I going to lose it to just heat, or am I going to get some work out of it? All right, so heat and work are going to be very different based on the pathway. The overall change in energy is exactly the same. All right, So if we change the heat of a system, we are going to affect the temperature of the system. All right, so here's our equation that allows us to calculate our heat. So Q is our heat. Q is proportional to the change in the temperature. Meaning if I put in 10 joules of heat, I'm going to see some amount of temperature change. If I put in 20 joules of heat, I'll see a doubling of that temperature change. All right, so it's proportional, and we can see that down here on the graph. As I put in energy, I see temperature changing, and it's going up in a straight line. The straight line, the slope of this straight line, is represented by this value called C, and C is the heat capacity. All right, so C is our heat capacity for the substance. So this number is going to depend on what substance you're using. If you're talking about heating water, or if you're talking about heating a metal, it's going to have different heat capacities. Every substance has a different heat capacity. Heat capacity is constant depending on the substance. All right, so before we go more into this equation, I want to talk about how we measure temperature. 3 most common temperature scales in the United States. Fahrenheit is the most common one used that probably everyone is familiar with. And that's the first one given up here, where we sort of have arbitrary numbers to represent the freezing and boiling point of water. Most common that you'll probably see in the lab, in a science lab, when you're actually measuring anything with a thermometer, is going to be Celsius. Celsius sets the freezing point of water at 0 and the boiling point of water at 100, and everything else is relative to that. When we look at doing calculations, so using temperature in an equation, we're going to see Kelvin. Okay, and that's this bottom scale. Kelvin does not have any negative values. If you look over here, absolute 0 is 0 Kelvin. And this is where all motion stops. All electrons stop moving. So there's nothing colder than absolute 0. There's no motion below absolute 0. And so we set that as a definite reference point. Therefore, all Kelvin temperatures are positive. This is very useful when we're looking at using temperature in a calculation. So we're going to focus on this semester looking at Celsius and looking at Kelvin. So frequently you'll see temperatures given in Celsius because in the lab this is most easy to work with, but we'll be doing calculations with Kelvin. Now, between Celsius and Kelvin, you'll notice that their units are identical. So 5 degrees Celsius is going to be 5 units of Kelvin as well. That's not true with Fahrenheit. Fahrenheit has 9 degrees per 5 degrees of Celsius. Alright, so that gives us our conversion equations up here between Fahrenheit and Celsius. You're not required to know these, but I wanted to point out you can convert between the two. It's just not nearly as straightforward. It takes a little bit of thinking. But conversion between Celsius and Kelvin is pretty simple. We take the Celsius value, add 273.15, because that's what lines up right here, and that gives us the Kelvin value. Alright, so that one you are going to need to know, but that one's pretty simple. Alright, so back to our heat capacity then. Heat capacity is a constant value depending on the substance. There's a couple different ways to refer to it. Heat capacity in general is written as C or sometimes CP for capacity, and it's the amount of heat needed to increase the temperature of a substance by 1 Kelvin or 1 degree Celsius. How much heat do I have to put in terms of joules or kilojoules to raise the temperature 1 degree? Alright, within that heat capacity definition, there's more specific terms. Specific heat capacity is the heat capacity of 1 gram, or sometimes 1 kilogram. You'll see the units when you look at the value. This means how much heat do I need to raise the temperature 1 degree if I have 1 gram of the substance. And then molar heat capacity, the heat capacity of 1 mole. How much heat do I need to raise 1 mole of a substance 1 degree? So whether you're using specific heat capacity or molar heat capacity really only matters based on the units. You want to pay special attention to the units you see for your heat capacity. Alright, this one's specific heat capacity because we're looking at kilojoules. So the amount of heat, or joules, needed to increase 1 kilogram of a substance 1 degree Kelvin. This table shows you some examples of heat capacities for different substances. So we have a variety of metals over here on the left side. We get into some non-metals, diamond, granite, sand, even gases can have heat capacities. And then different materials that people might use for building. So we can see the heat capacity can vary wildly based on what the substance is. If you look down here, water has an extremely high heat capacity. The very high heat capacity value is what makes it very unique and very valuable for the basis of living organisms. We use water in order to maintain our body temperature. Right? If it didn't take a whole lot of heat in order for water to turn into gas, we wouldn't be able to keep it in our bodies for very long. We use water to carry away toxins. We use the mechanism of sweating to try to carry away heat because water can carry so much heat. Alright, so if we think about our Q equation down here then, Q is proportional to our delta T, right? And here's our heat capacity. One more thing we want to add into this is our M, and our M is going to be mass or moles. So this is essentially amount. How much do we have? Whether you use grams or moles is based on the units of your heat capacity. Are you using specific heat capacity or molar heat capacity? Alright, but we need to know the amount. So over here in this picture we have some relationships. Alright, here's our Q. I have a certain mass of a substance to produce a certain temperature change. If I then put twice the amount of Q, so I put twice the heat in, that is going to give me twice the temperature change. Alright, so remember that proportionality. Alright, so back to our Q and our certain amount and our temperature change. If I double the Q, this could also produce the same temperature change for twice the amount. Alright, so now those are proportional. Alright, so if I put twice the joules in, I can either cause twice the temperature change, or now I am able to heat twice the amount of the substance to the same temperature change. But then in the third picture, we have our Q, we have our mass of copper to produce a certain temperature change. If I then switch it to water instead of copper, my Q is no longer proportional. So if I want my temperature change to be 10 degrees, and I have 10 grams of my copper, that will take a certain amount of heat, but 10 grams of water to change 10 degrees will take an entirely different amount of heat because the heat capacities are very different values. Alright, so keep that in mind. So when we look at heat capacity values, we can get an idea about how much heat the substance can hold. Alright, so heat capacity means the amount of joules or heat required to change the substance 1 degree. So the higher that heat capacity, the more energy is going to be required to cause that temperature change. All right, so if we look at these values, water, gold, iron, and zinc, we can see the heat capacity values given. Water has by far the largest heat capacity on this list. It is going to take the most heat to increase the temperature of the water compared to the others. Water can hold a tremendous amount of heat. Most metals, you'll notice, heat up very quickly. When you expose them to increased energy and put heat into metals, their temperature changes dramatically and they heat up very fast. Water heats up much less with that same amount of energy. All right, we're going to do a few examples using this equation so that we can calculate heat, we can calculate amount, we can calculate heat capacity, and we can even calculate temperature change. All right, so we're using our equation Q is equal to mCp delta T. All right, so in this one, calculate the number of joules. So joules is going to be our heat, our our Q, needed to warm 100 grams. All right, so 100 grams is going to be our amount of water from 25 to 80. So here's our temperature change information. And the heat capacity is given for us. All right, so we're solving for Q. We're going to use 100 grams, our heat capacity for water. And notice the units, joules per gram, degrees Celsius. So I have joules over here for my M. I have grams over here for my M. I have grams over here for heat capacity. Those have to match so that the grams will cancel out. All right, so make sure you look for the units. And then our delta T. Delta T we're going to define as final temperature minus initial temperature. So it says that our water was heated up from 25 to 80, so 80 is our final, and 25 was our initial. All right, and this is degrees Celsius, which will cancel out with my temperature units, and I'll be left with joules. All right, so if we do our math here, I get 23,012 joules for our heat. All right, and notice this is a positive value. So remember, positive Q means that heat is going into the system. And that's what we see because the water is increasing in temperature, so heat had to go in. All right, let's look at the second one. Calculate the number of joules, so that's our Q. Released. All right, so that means heat is leaving our system. We have 52.5 grams of water. We're going to use our same heat capacity again because we're looking at water. And this time it's being cooled from 95 to 28 degrees Celsius. So here's where I do final minus initial. So the final this time is 28 minus the initial is 95. All right. So again, my grams will cancel out. My Celsius is going to cancel out, and I'll have joules. But notice this time, I'm going to get a negative number when I do my math. All right, and the negative number is coming from the temperature change. All right, because 28 minus 95 is negative. So remember what the negative means. If I have a negative Q, that means heat left the system. All right. So we can calculate for Q, or our joules. We can also calculate amount. So in this question, we're going to be looking for mass. We have zinc, specific heat of 0.386 joules per gram per degree Celsius, released 1,964 joules of heat when it was cooled from 92.5 to 65 degrees Celsius. What was the mass? All right, so same equation. This time we're solving for the mass. So we know Q. And our Q is coming from here. Released means a negative sign. Alright, so heat is leaving our system. We're solving for the M. We're given the heat capacity. And we're giving our temperature change. It's cooled from 92.5 to 65, so final is 65 minus initial. Alright, notice we're going to get a negative here because we're cooling our temperature. We have a negative over here because heat is released. Those negatives are going to cancel out because remember mass has to be positive. Alright, so we're going to take the negative 1964, divide by the heat capacity, divide by the temperature change, and we get 185 grams of the zinc. Alright, so we can solve for Q and heat. We can also solve for mass if we know our other values. Alright, the last one we're going to look at for this is solving for heat capacity. We can use calculations of heat capacity to identify a substance. If we don't know what it is, we can use heat capacity to try to narrow it down. In this one we know what it is, but we're going to calculate heat capacity, specific heat of platinum. We have 1092 joules of heat released. Okay, so again that's the negative. When we have 125 grams of our platinum and it's cooling. Alright, so heat capacity is what we don't know, what we're solving for. Now it says platinum was cooled a total of 65.2, so this is already delta T, but I'm going to make it minus because it was cooled. Alright, and that means that my minus over here and my minus on the left are going to cancel out. Heat capacity is a positive value. Alright, so when I divide my joules by the mass and then divide by the temperature change, I get a heat capacity of 0.134. There we go, 0.134. And this is joules per gram per degree Celsius. Alright, so we can solve for several things using that same equation. Alright, using the same idea. Alright, we're not venturing away from our equation yet. Using the same idea, same equation, we have what's called thermal energy transfer. And this is the idea that heat transfers from a hotter object to a colder one. So if I put a heated object in proximity of a cooler thing, I know that heat is going to transfer toward the colder object. Alright, we can use this idea to calculate a few different variables, just like we were doing before. Alright, so let's read through this and look at what's happening. We have 175 grams of a metal that is heated to 93.5 degrees, so hot metal. We're going to then put it into 105 grams of water at 23.5 degrees Celsius. So the water was pretty much room temperature. We're putting a hot piece of metal into it. We have a perfectly insulated container. Okay, that means heat is not going to be lost to the surroundings. We can't lose heat to the beaker or the table or the air around it. Alright, when we put our hot metal into the water, the final temperature of the water-metal mixture, after we allowed it to transfer the heat, was 33.8 degrees Celsius. Alright, so the heat from the hot metal transferred to the water, and that raised the temperature of the water. We want to find the specific heat of the metal. So as I was saying before, this is a common experiment to try to identify metals or other substances using specific heat values. Alright, so this is going to rely on a couple of ideas. The first, we have a certain mass of this metal at a certain temperature. we have a certain mass of the water at a certain temperature, and we're going to put those two together. All right, that means that the metal is going to lose heat. All right, so we're going to have a negative Q from the metal, and the water is going to gain heat. All right, the amount of heat lost by the metal is going to be equal to the amount of heat gained by the water. All right, we can also look at this as Q of the system is the negative Q of the surroundings. All right, whatever happened to the system, whether heat was gained or lost, is the opposite of what happened to the surroundings. So we're going to use that idea and set up an equation. All right, so I'm going to put the equal sign in the middle. I'm going to put my information about the metal on the left side, and I'm going to put the information about the water on the right side. All right, so on my metal, I'm using my Q is equal to M times Cp times delta T. My M was 175 grams. We're trying to find the heat capacity and the temperature change for just the metal. We started at 93.5. We ended at 33.8. All right, so that's what happened to the metal. On the other side of the equals, I'm going to put what happened to the water. So the water, we had 105 grams. Heat capacity of water, 4.184. And the temperature change, 33.8 minus, and this one started at 23.5. All right, water was receiving the heat, the metal was losing it, so I'm going to put a negative out here in front of the metal. All right, so this will then create an equation that allows me to calculate the heat capacity, because I don't know what Q is. I don't know what the joules were. But by calculating the Q that water gained, because I have all the information for that, I can use that same Q to represent the amount of heat the metal lost. All right, and this next slide shows that written out. All right, so we have the information about the metal on this side, our grams, our variable. The only difference is in this way that they did it, they flipped the final and initial temperatures so that they didn't have to put a negative out front. All right, they're just keeping everything positive. But then on the water side, they have the 105, her heat capacity. Here's our temperature change. All right, so when we simplify this and solving for our variable, we can then calculate the heat capacity for the metal. All right, so what we did here, everything on the water side is a real number, and then we're going to divide by the 175 and the temperature change to get us our heat capacity, the 0.43. Alright, so let's try one like that. We're going to put 225 grams of aluminum at 85 degrees Celsius into 115 grams of water that starts out at 23 degrees Celsius in our insulated container. Final temperature 41.4. What is the specific heat of the aluminum? Alright, so again we're going to set this up using our equation. So I'm going to put the metal on this side. So we have 225 grams of the aluminum. I don't know the heat capacity, that's what we're going to look for, times the temperature change. Now just the aluminum started out at 85 and it went to 41.4. Alright, and now on the other side I want the water, 115 grams times my heat capacity of water, which you will probably have memorized by the time we're done with all this, and then our temperature change. So 41.4, but this one started at 23. All right. So our heat capacity. We're going to multiply everything on the right side together. So I get 8,853.344. And we're going to multiply the 225 times the temperature change on this side. And that was 9,810. And then when we calculate that, we get 0.902. Alright, and this was measured in terms of joules per gram per degree Celsius. Alright, so we can calculate the heat capacity of our metal, whether we know its identity or not, based on this thermal energy transfer. Alright, the last part we want to do is we want to talk about work. Since we've talked about heat, we talked about Q, now we want to focus on the work. Now we're going to focus on work done by gases, so compression or expansion of gases. So this is our equation that defines work. Work is equal to negative P external, so this is pressure, external pressure or atmospheric pressure, times the change in the volume that the gas occupies. Alright, so we're going to focus on the gas doing the work or work being done to the gas. Now also notice there is a negative out front here. Alright, remember a negative W means the system is doing the work. So if our gas expands, pushing against an external pressure, the system or our gas is doing the work, so we're going to end up with a negative W. If our gas compresses because some other surrounding force is pushing on it, then the surroundings are doing the work. And we're going to end up with a negative delta V, negative change in volume, times the negative, making the W positive, indicating the surroundings are doing the work. The other thing we want to look at is our units. When we're doing pressure, pressure is measured in atmospheres for this equation. Volume is measured in the liters for this equation. So when we multiply pressure times the volume change, we get liter atmospheres. That is the unit. We want to convert that into joules in order to get energy units. Alright, so work in terms of energy. Alright, so here's our examples. We have a piston pressing against an external pressure, 15 atmospheres. So that's our pressure that we're going to put into our equation. How much work is done if the cylinder increases from 0.15 liters to 0.48? Alright, so here's our equation. Work is negative P times change in volume. So we have negative 15 atmospheres times change in volume is the same as our change in energy. We're going to do final minus initial. So 0.48 minus 0.15. Alright, when we do our calculation, we get negative 4.95 liter atmospheres. If I then multiply that by the 101.3 joules per liter atmospheres, we can convert it into joules. So I get negative 501.4 joules. All right, remember the negative means the system is doing the work. All right, so that's what we're asking here. Is the system doing the work? Why, yes it is, because there's a negative sign there. All right, the gas is expanding, pushing against the pressure, therefore it's doing the work. All right, let's look at the second one. What is the work done if a piston with an initial volume of 4.5 liters contracts to 1.77 liters? So now the volume is getting smaller, and we have an external pressure of 1.34 atmospheres. Alright, so 1.34 atmospheres for our pressure. This time when we do final minus initial, you'll notice we get a negative number. The negative times the negative is going to make it positive. So I get 3.66 liter atmospheres. Positive value because the surroundings are doing the work on the system. Now I can convert that into joules by multiplying by our conversion factor. And I get 370.8 joules. Alright, positive value because the surroundings are doing work on the system. Alright, one last example. We're going to put everything together. We're going to go back to our equation that energy is equal to heat plus work. So instead of just calculating Q or just calculating W, we're going to look at both of them and then figure out how that affects E, or energy. So now we have a balloon filled with a gas. Gas is expanding its volume by 2 liters. Alright, so there's our work part. The pressure outside the balloon is 186 millimeters of mercury. There's our external pressure. And the energy change, or our delta E, of the gas is 450 joules. How much heat did the surroundings give the balloon? So we are looking for the Q. Alright, we know the E because the E is given for us, 450 joules. We need to calculate Q so that we can then, we need to calculate W so that we can then find Q. Alright, so our W is our negative P times delta V. We know our delta V part. That's the 2. We're given the external pressure, but we have one little problem. We need this to be atmospheres. Alright, so 1 atmosphere is 760 millimeters of mercury. So I'm going to convert my 186 millimeters of mercury into atmospheres. Alright, so when I do that, I get 0.2447 atmospheres for my pressure. Alright, so filling this in, W is negative 0.2447 times the 2 liter change that we saw before. We have a negative value, so negative 0.4895, and this is liter atmospheres. Now you'll notice my energy is in joules. So I need to convert my W into joules so I can put them into the same equation. So same idea. We're going to multiply the liter atmospheres times the conversion factor, 101.3 joules per liter atmospheres. And we get negative 49.58 joules. Negative because our system is doing the work. So we're going to then plug this in. So I have 450 joules for my E. trying to find Q, and my W is negative. Alright, so if we then solve for Q, Q ends up being 499.58 joules. And Q is positive because heat is going into the system. Alright, so we can calculate Q independently, we can calculate W, we can put them together into the energy equation to look at the change in energy for the system. And we can use this equation to find energy, to find Q, or to find W.